Welcome everyone. Today we're going to look at graphs of motion, but only graphs of motion for vertical motion, and it's actually lots of fun. So, have you ever thought about how graphs can be useful when describing the motion of an object? We've done the equations, but sometimes the equations are difficult to imagine what's going on. When we have graphs, the graphs give us a much better picture, and we can get information from the graphs, okay? So, we've looked at, through the series so far, definitions, equations, acceleration. Today we're going to look at graphs. So our keywords are velocity, which hopefully we know what that is, displacement and position. We're going to look at acceleration due to gravity, and then of course direction. Direction, 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 direction. If there's something that's going to make you make a mistake, it's going to be direction. So we've got to be very clear on our directions, okay, because we're dealing with vectors. So when we look at the graphs, we're going to have three types of graphs. We're going to look at velocity time graphs, which are always curves. We're going to look at velocity time graphs, which are always straight lines. And then the nicest out of all of them is acceleration versus time, because the acceleration we're working with is constant. It's 9.8 meters per second squared down. So it makes that graph really, really nice, and we hope we get asked one of those. Let's look at a position time graph. We're doing sketches, so please, you really do need to use a ruler. I can't on the board. So we always have time, and we have position. Now, depending on which direction I take as positive, that's going to determine whether the graph sits above the x-axis or below the x-axis. So let's take up as positive. Okay, as we take up as positive, let's pretend that I'm throwing an object up. It's going to reach the top of its motion, and then it's going to come back down and go below where I threw it from. And where we threw it from is my zero position. So the motion is going to be this. My object starts at naught, oops, and then as it goes up, it gets slower and slower and slower and slower, and then it reaches the top of its motion. What I need you to see is that as it goes up, the gradient gets less and less steep. The gradient's getting less steep because it's slowing down. So it's covering smaller time distances in the same time period, but it's slowing down. And then it gets to the top of its motion where the displacement doesn't change, just for a fraction of a second. Now it's going to come back down. As it comes back down, it gets faster and faster and faster and faster. Now, if it goes past where it started, it'll just keep going straight. What are we looking for? Is realizing that as it goes up and it slows down, the gradient of the graph gets less steep. As it comes down and speeds up, the gradient gets more steep. This is nice because it looks like the motion of an object being thrown up. If I change down as my positive direction, still, now I've got to go below the axis, gets slower and slower and slower, so the gradient changes, gets less steep, gets to the top, and then it speeds up. Now, it's not quite the same. It should cross the same place. Doesn't matter. The gradient gets more and more steep as it gets faster, less and less steep as it gets slower. I'm not worried about whether it's a positive gradient or a negative gradient because it all depends on which direction I took as positive. It's quite nice, okay? Then we get our velocity versus time graph. And the nice thing about these is that it's always straight lines. Now, whether we start at zero or at another point with a velocity all depends on whether we threw it up, whether we dropped it, anything like that. So let's just take it as having dropped. I'm going to take down as my positive direction for the first time. And what happens is that it's a straight line. Why? Because the acceleration due to gravity is a constant. I can get acceleration from the gradient of this graph. and it's always going to be a straight line. If I take down, up is positive, all that happens here is now my graph's going to go that way, still a straight line. Gradient of the graph is acceleration, and we can find displacement by looking at the area. And lastly, if we look at the acceleration time graph, this is the nicest out of all of them, always a straight line. If we have down as my positive direction, it's just going to be that, and we know that this value is going to be 9,8. If up is my positive direction, then this is minus 9,8. It's a constant. Makes our lives very, very easy. So, when we look at the graphs, okay, we've got velocity time, displacement time, position time, acceleration time. Shapes are the same. We just need to be able to put them into different contexts. Right. We're going to take a short break, and I'll see you in a couple of minutes. Welcome back. Now we're going to look at graphs in detail, because just doing the basic shapes doesn't always make sense for us. Okay, so we're going to do a little bit of a case study. So what we're going to do is we're going to consider a small ball that's projected upwards. In other words, I've got a ball and I'm throwing it, okay? And I know for some of you that you don't like this whole thing because you go, what about when the ball's in your hand? We're considering, yes, my hand has to exert a force on the ball, but I'm looking at when the ball leaves my hand, okay? Then my hand's no longer part of the issue, and it's moving just under the force of gravity, okay? So that's what we're looking at. So we have a small ball that we're going to project upwards, and I'm telling you that I'm throwing it upwards at 19,6 meters per second. So that is my initial velocity. That's not going to change. That's going to be the velocity for this whole, the initial velocity for all of it. So I am now going to want to draw a velocity time graph. What I have here is a whole bunch of times. We want an accurate graph. So I need to know what the velocity of the object is. We're going to take up as positive. Okay, we're going to use that the whole way through, which means for me that acceleration is minus 9,8. That's important because the object's going up, acceleration comes down, so that means as it goes up, it's going to slow down, and maybe somewhere along the line it's going to stop, and then it's going to come back down, okay? I'm not assuming for all of this that it's just going up the whole time. I'm going to have to see. Right. Initial velocity was 19,6. I need to calculate the velocities for all the rest. Thinking about the information I have, I'm going to use this equation. Whoops. If I write it correctly, that's always important. VF equals VI plus A delta T. Now what's going to stay the same is the fact that that's 19,6. This is minus 9,8. And for each of these equations, I'm going to change time. First one is at 0,5. Right, so we need to have our calculators. Let's just put that here quickly. So we've got 19.6 plus, and it's going to be minus 9,8 times 0.5. And remember, we can't work with it as a fraction, so we get 14 comma 7. So I'm just going to put that in there, all right? Now, what we're going to do is instead of a half, this becomes 1. Okay, so if you look carefully on your calculator, the really nice thing is we can just go back there and I'm going to put a 1 in instead. And now we get 9,8. So it's quite a big change compared to the first one. I'm going to do the same thing now. And instead of that, I'm going to put 1.5. And I know this feels quite tedious and laborious, but it's actually quite important. So we're going to go back there. I'm going to make that 1.5. Oops, no, I don't need that second bracket. There we go. We now have, oops, that's what I want, 4,9. So we're starting to see in 1.5 seconds it's changed quite a bit. We need to go back here. Instead of 1.5, we now have 2. Go back to our calculator, and we're going to change that to a 2. Oh, 0. So, after 2 seconds, it's reached the top of its motion. Okay? Now, we need to look at what happens after that. So, our assumption is that now it's going to come back down. Up was my positive direction. So it means that now I should be getting negative velocities, okay? So let's see if that's what happens. So again, we're going to go here. We're going to change that to 2.5. Let's go to our calculator. 2.5. Oh, look, minus 4,9. I'm hoping some of you can see what the trend here is going to be. If I now take this and make it 3, there we go. I'm hoping some of you can take a guess as to what my new value is going to be. Ooh, minus 9,8. Are you starting to see what's happening with these values as I go down? That there's some sort of symmetry, but that's good. It's what we want. Then we need to do 3.5. There we go. So we put this into our calculators again. Okay, close my bracket. Oh, look, 14,7. So what do we think is the very final velocity going to be? If we look at the trends, okay, it went 19,6, 14,7, 9,8, 4,9, 0. Then it started again, minus 4,9, minus 9,8, minus 14,7. So I'm going to make a prediction, and I think that this final one is going to be minus 19,6. Let's just check though, because you never know. So over here, we're going to put 4. Let's check. Let's get rid of that. Times by 4. Oh, look there. 19,6. I'm happy with that, because by now you've been told that the velocity I throw it up with is the velocity I'm going to catch it with, as long as it's at the same place. Okay? That's the important part. We're now going to take this and put it onto a graph. So we're going to draw an accurate graph. So here we go. I probably haven't made my graph long enough, but it's all right. There's delta t. There's v. Now, for me to do it completely accurate is a little difficult on the board because I don't have a ruler. You really do need to practice doing this properly. So we had time frames that were 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay? Now, if we go back to our values, they're changing by 4,9 every time. So this is a graph where I can use 4,9 as my scale, but we wouldn't normally do that. We'd go 5, 10, 15, etc. But this one, because if you go and minus, so this is a little bit of a trick here, if I minus those two together, I'm going to get 4,9. If I minus those, it's 4,9. Minus those, it's 4,9. So the velocity is changing by 4,9 every time, okay? And we're okay with that because it's half a second. That means when I get to my graph, I can go, 4,9, 9,8, 14,7, 19,6. Minus 4,9, minus 9,8, minus 14,7, there's a minus there, and minus 19,6. Okay, I've got all my points, don't forget your 0. This is an accurate graph, so you would plot it nicely. So you would go, we're starting at 0, my time was 0, so there's my, there's my first point. At half a second, it was there. At 1 second, it was there. At 0. Okay, this graph is very not accurate because you can see it's already going to become a little bit of a curve because my spaces aren't the same. But you get the idea of what we want to do. And what we're going to get is this. So let's get rid of those really bad marks because they're not working so well. Okay, and my graph, and went past there and down to here, and at 4 seconds, it was here. It's a straight line, and I know for some of you, you're going, but it changed direction. Why did it keep going down? Because it changed direction. Okay. Yes, it was speeding up. Negative is a direction. Negative here doesn't mean slowing down. Negative means I've changed direction, but you can see the velocity gets bigger and bigger and bigger. Okay? So on this graph, what I can see is that my object went up, stopped, came back down. I chose up as positive. So this graph gives me a nice idea. It's a nice straight line. I'm always going to get straight lines. The gradient of this graph must give me the acceleration of my object. And the area under the graph tells me how far it's gone. So when we look at this and we go, this area, and it's a triangle, remember that's a half base times height, gives me the distance. If I want the total displacement, I have to add it to this area. But that area is negative, and the two will cancel out. Gradient, which gives me the acceleration, is the change in the y value, which is v, divided by the change in the time value. Please be careful with these ones because what happens here is, say I use a point that's 0, you don't show the 0 in your calculation and then you run into trouble. If you're working out a gradient, I must have 2 points. Even if one of them's the origin, I still need to include it in my calculation because I'm working out a gradient. It's a change in. So I have to show the two things I'm comparing or changing in from. Okay? Now, let's look at the position time graph. So again, I'm taking up as positive. I can't change my sign convention. Okay? You just can't. So we're now realizing that we're going to use VF equals VI. Oh, no, we're not using that one. Again, apparently my brain has gone on strike. So we're going to use delta Y equals VI delta T plus a half a delta T squared. Okay? And we would do exactly the same thing as we did last time. Now, first of all, position when it's 0 is 0. It hasn't moved, okay? What will happen here is we're going to go, whoops, no, we're not. Apparently it doesn't like me. So 19,6 times 0,5 plus a half minus 9,8, 0,5 squared. I'll stretch. Okay, so we put this into the calculator just quickly because I want you to see it. We're going to, okay, so we've got 19.6 times 0.5 minus 0.5 times 9.8, oopsie, not 98, times 0.5 squared, oopsie, maybe I should put a 5 there, so what happens when you're in a hurry, and we get 8,57. Now, I'm about to run out of time, which is not a good thing, so you would need to do all of this, okay? When you plot this graph, and you'll do it accurately for me, you're going to see this. None of your positions are going to be negative. You're only going to get positive answers. They're going to get bigger and bigger and bigger. Then they're going to get smaller and smaller and smaller till they get to 0 again. It doesn't go below the line because I didn't change direction. Well, I did change direction, but I didn't go below where I started. Okay? And now, so we get a nice curve, okay? So I'm going to leave that to you. You need to just work through that. It's important to do these accurate graphs. The nicest thing about this is I chose up as positive, so I don't actually have to work out my acceleration because it's constant. So my acceleration graph will be drawn at minus 9,8. There we go. It'll just go across and end at 4 seconds. That's all it is. Acceleration due to gravity can't change direction, okay? So we've got this nice graph, nice and straight, and if I had to calculate the gradient of my velocity time graph, that's the value I would get. That's where we're going to end it for now. We're going to take a short break, and I'll see you in a couple of minutes. Welcome back, everyone. Now we're going to dive into some questions because that's the best way to learn, is to just practice and practice and practice. Okay, so here we go. I have a ball that is thrown up from the balcony of a building. The ball reaches its highest point, then falls to earth after passing the balcony on the way down. Now they want us to draw a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. What they haven't said to me is which direction we want as positive. That makes a difference. So now we got to be careful. We need to make a decision and stick to it. We can't change halfway through. In some questions, they'll say to you, they'll go, this is the direction we want as positive. That's the direction you must work with. I like to draw a little sketch so I know what they're saying. So they're saying to me, I've got a balcony, the ball gets thrown up, and then it comes back down. They haven't given me values, they haven't told me anything about that. So what we're doing here is they just want the shape. Now, if I have a choice, I like to take original direction of motion as positive. So for this one, I would like to take up as positive, which means acceleration is minus 9,8 meters per second squared, and it's minus because it's going down. So let's draw the position time graph. Position, which is m, okay, time in seconds. Now, I don't have any more detail. It's a sketch. What are we looking for? Shape. I've taken up as my positive direction. That means my graph, the 0 point is the balcony. It's going to go up and get slower and slower and slower. Then it gets to its highest point, then it gets faster and faster and faster and faster, and it goes below here. This is what they're looking for. Gradient getting less steep, gradient getting more steep, and going past where it started, because the final displacement is going to be negative. It ended below where it started, and I said up was positive. So it's got to have a negative displacement at the end. That's very important. Now they want the velocity time graph. Okay, so velocity time. What happened to the velocity? Well, I threw it up, so it had an initial velocity. That velocity got smaller and smaller and smaller, stopped, changed direction, and came back down and got faster and faster and faster. So I know this has to be a straight line crossing the time axis, but here's the trick. Here we go. Crosses the time axis, but the second part, this part of the graph, must be longer than the first part, because it went further than when it started. So we've already done the fact that if it goes up and comes down to the same place, the velocity is the same when it leaves and gets here. But now it goes past that starting point. Because it's going past that, it's going to go faster and faster and faster and faster. So it's still a straight line because my acceleration is constant. That gradient is my acceleration, and that's the same for the whole way through. The issue is how long it goes for, okay? Then we get to the easiest out of all of these, which is my acceleration time graph. We like these. So, time, acceleration. Now, I'm hoping what you guys have noticed every time I do one of these sketch graphs is I always label the axes, okay? You must label the axes, otherwise it's just random lines. It doesn't make any sense. I can't get anything from it. So make sure you label your axes. You only need to put values on your graph if you know values. And if they ask you. Sometimes they don't want the values. All they want to know is, do you understand the shape? So be careful. Don't put extra stuff on the graph because you're going to waste time calculating stuff that you don't need. But don't stress that you don't know the values. We're looking for the shape. We're looking for whether you understand the motion through the graph. Now here, I can put a value on. Because I know acceleration due to gravity is always the same, I took up as positive. So I know that's minus 9,8. That's a given. And it's a straight line. No matter what happens, it's a straight line, which is great. We like this. This is nice and easy. Okay, so here we go. Next one. A man fires a projectile. It can be anything, okay? Vertically upwards, there we go, with a velocity of 29,4 from the edge of a cliff. So again, I've got the edge of a cliff, he's thrown it up, and then it comes back down. The height of the cliff is 100 meters, so that's going to be a displacement. After some time, the projectile lands on the ground below the cliff. The velocity time graph, which you'll see next, shows the motion, and it's not drawn to scale. They put that in because sometimes we think when we get a graph in an exam or a test, or we look at it and we go, it's not quite, doesn't feel like it's right. It's okay, it's not about that. You're going to get important pieces of information from the graph, and that's what we're using. So here's the graph. So this is what we know. Initial velocity, 29,4. They're saying to me over here that that's how long it takes to get to its highest motion, and then it carries on down. What they're telling me in this graph without putting it in words is they're telling me which direction is positive. Here, they tell me initial velocity is plus 29,4. I know I threw it up. I have to take up as my positive direction throughout this question. I don't have a choice. And this is why I don't want you to learn that down is always positive or up is always positive, because then when they change in the question and they decide what is positive and negative, it gets a bit confusing. So make sure you can work with both, okay? So, question says, use the graph, very important term, use the graph. Maybe I should have a pen. Use the graph. Use the graph means calculating area or calculating gradient, okay? You cannot use equations of motion. If it had just said determine, you can do it how you like, or calculate, you can do it how you like. Area, gradient, equations of motion doesn't matter. But they said use the graph. They are specifying the way they want you to do it. Why? Because we're testing a skill. We're testing an understanding. Okay, it's not just to make your life difficult. Okay, it really isn't. So, use the graph to determine the time that the projectile takes to reach its maximum height. Actually, we can just read it. 3 seconds. No calculation needed. Bonus. We like those. Calculate, and we're using the graph for all of this, the maximum height the projectile reaches above the ground. That is this area. Okay? So we want delta y, which is the area under the graph, which is now a half times base times height. So it's a half. My base is 3. My height is 29,4. I most certainly cannot do this in my head. So I'm going to, let's get rid of this. A half times 3 times 29.4. And I get 44,1. That's nice. Not so bad. Oops, I'm going the wrong way. Then they want the sketch of the time graph. Well, we know how high it went. Okay, it took, so this is my position time graph. I know it went up and it came down. There's my 6 seconds. There's my 3. They didn't ask me to put the value in, so I'm not going to worry about it. And that gets us to the end of that one. Wasn't as bad as it sounded, correct? So we're going to take a short break, and I'll see you in a couple of minutes. Welcome back, everyone. I hope you're ready to do some more questions. I really enjoy these questions, in case you hadn't noticed. They're lots of fun. So, here we go. We have a ball projected vertically upwards, in other words, thrown, with a velocity of 16 meters per second from the ground. Ignore the effects of air resistance. Use the ground as 0 reference. What does that mean? That means that we compare everything to the ground as my 0 point. So everything above the ground is either negative or positive in terms of displacement. Everything below the ground is negative or positive. Okay? Below the ground would be hard because it's the ground. They want us to calculate the time taken by the ball to return to the ground, and then they want us to sketch a time velocity graph. First decision we have to make, which direction do we want to take as positive? I always take original direction as positive. So here we go. My initial velocity is 16 meters per second. I'm going to come back to my final. My acceleration is minus 9,8 meters per second squared, and we want a time. Here we now have a choice because we know the ball's going to go up, it's going to stop, and it's going to come back down and hit the ground. Here we need to be careful. You are very welcome to calculate the time it takes to get to the top and then times the time by 2. But I want to show you what makes vectors so special is the fact that if it leaves the ground at 16 meters per second, it's going to hit the ground at minus 16 meters per second. Okay? You can see that in graphs when you do them nice and accurately. And why? Because throughout the motion, it's experiencing the same acceleration. If the acceleration changed, this wouldn't be possible. So that means if I take the whole motion into account, I can do this in one step. If I make final velocity minus 16, okay? Because watch. If I now do, the easiest equation is going to be VF equal to VI plus A delta T. So I have minus 16, 16 minus 9,8. At this point, I need to calculate time. If I calculate time and I get a negative answer, I have made a mistake. Time is a scalar. As much as we would love time to go backwards, it can't. It doesn't have a direction. Time is just time. So that means when I do my calculations, I must get a positive time. So that's a check for you. If you get negative time, you've made a mistake with your signs. So to get this time on its own, I'm going to take the 16 over, so I'm going to get minus 32 minus 9,8 delta t. So now I'm going to have to go minus 32 divided by minus 9,8, which I can't do in my head. So minus 32 divided by minus 9.8. And I get 3,2. Remember, we round off to 2 decimal places. So that's going to be 3,27. 3,27 seconds. So I know it takes 3,27 seconds for it to get up and come back down. Nice and simple. We can do this. The next question says they want to sketch the velocity time graph. What I want us to do on this graph is I want us to put the values we know. So I want initial velocity, I want final velocity, and we're going to look at some times. Okay, so you get used to the way they can ask it. We have straight lines because you're going to use a ruler. Time, velocity. And now what we knew, let's close my bracket, is that it left at 16 meters per second. It hit the ground at minus 16 meters per second. So my graph does this. I also know that this time is 3,27. What I could have also asked you is, what is the time it takes to get to the top of its motion? That's quite nice, because now I'm going to take 3,27 and divide by 2, because it's the same time up as down. So I'm not using the whole decimal, because I've now rounded it off. So 3.27 divided by 2, and I get 1,635. When I put the 1,635, I have to keep all 3 of those decimals now, because it's exactly halfway. I can't round it off, because then what we're saying is that it's just a little slower to get up than it is to get down, which isn't true. It's the same to go up, same to come down. So just be careful with that one. This, if I ask you a question like this, where it's not just draw the sketch of the shape, it starts to become worth a few more marks, because I want to see whether you can take the information you found and make sense out of it. Okay, so that's what that question is. Right. Okay, the 2 velocity time graphs are for the 2 objects A and B falling vertically. Both objects start from a height of 8, strike the ground at the same time. So here's our graphs. Which one of the graphs was projected? Which one was thrown? Now, if we look at it, it's got to be A. Why? Because it has an initial velocity. I don't care that this time is different. All that is telling me is that B was dropped, and a little while later, A was thrown. That's all. Okay? Now they say, calculate T. Okay, I want that time. Now, here life gets a little interesting for us, because we don't actually have, well, they start from a height of 8, okay? This isn't really so difficult. They both started from 8, which means, well, this is not a nice question actually. That area gives me a value of 8. And if I take the area under this graph here, that's also going to give me 8. And I'm going to have all sorts of things. I probably should have given you a little bit more information. But what I need you to see, and I'm actually not going to finish this question, I'm going to leave it for you to sort, is that the area of the first object is equal to the area of B. Okay? Here, I really should have given you more information, because I didn't. Finding these areas is actually going to be quite difficult. I needed to give you something else to help you. What I do know is that B hits the ground with the same velocity as A. So this question, as it's given to you, becomes like a level 4 question. It's actually quite difficult. Simultaneous equations. But what I needed you to see here is that the areas are the same. So even though I've got a couple of unknowns, all right, I can still create 2 equations. And by doing that, I can get rid of 2 of my unknowns, okay? So then they wanted V. I can't find V until I know time, because once I know this time, it's going to be part of the simultaneous equations we did to get time. Once I know time, I can work out velocity, because I know the area of B. Okay, so the velocity would be the height. Might have been a little difficult to put in here, sorry. Okay, how does the area, and that's what we've just done, the areas are the same. Why? Because they fell the same distance. Their displacement is equal, so their area is equal. Okay? They want the magnitude and direction of the vector represented by the gradient. Well, minus, well, it's 9.8 meters per second squared, down. It's acceleration. Sure. I did do a difficult question there, but sometimes you got to see them because they're important, okay? Hopefully, graphs are a little easier now. Hopefully, sometimes you've got to go back and think about it, but that's where we're going to end it for today. So I will see you next time.